Now, equipped with knowledge of convolution and Fourier transform, we go back to analyzing what happens when we integrate over a cell window when we acquire the image. We said that this operation of actually summing all the photons coming into a certain receptive area and representing them with one value corresponds to this convolution. Now, assume that P of x is really symmetric around the origin. We can really say that this is actually a proper convolution. And we know that the convolution in space corresponds to multiplication in the frequency domain. So that basically means that we really need to look at the Fourier transform of this P, this rectangular box function, to really understand what's happening. The Fourier transform, or the modulation transfer function of the window function, can be computed quite easily. I wrote down the integral here, so P of xy is simply 1 in the sensory area and 0 otherwise. So around the integral, it's only 1 between w over 2 and w in the in the y direction, and h over 2 to h over 2 in the y direction. So if you take this integral, you'll notice that this is actually a 2D sinc function. So it's almost like a sine, but sine divided by its arguments. So what does this function look like? This function actually looks something like this, and this is in the Fourier transform domain. And the interesting thing is, this function is completely real. So there's actually no phase to this. That's great. Okay, so the magnitude is the same thing as the function itself. And somehow this doesn't. It is predominantly low pass, meaning that only at u equals to 0 and v equals to 0, and around that area, it achieves very high values. So if it's predominantly low pass, that I think actually means that it's blurring the image. What is more interesting is actually it has these intensity reversals, or in a sense, phase reversals for certain sinusoidals, or for certain frequencies in certain directions. Now, this is a bit more complicated to grasp. Let's see what happens in a very carefully drafted 2D image. So what I did here is I took this image on the left-hand side, and you see that it's actually formed of sinusoidals in the radial direction, and the frequency of the sinusoidals are actually decreasing as I'm going outwards. Now, I basically used a rectangular box filter to convolve this image with, which basically means that in the frequency domain, I multiply with this modulation transfer function. Now, notice that the first thing that we said was the modulation transfer function was predominantly low pass, which basically means that the high frequency areas in this image should be destroyed or should be suppressed when I actually do convolution with the rectangular the window function. And that's exactly what happens. The highest frequency areas, right seen in the center of this image, they're actually gone. They're really suppressed. So it only passes, low frequency areas. Moreover, it doesn't pass every low frequency area at the same time. It actually prefers certain directions. So what we see here, for example, the high frequency areas with sinusoidals that are horizontal and vertical in the image are actually preferred. They are passed, but sinusoidals that are in off diagonals, that are in the diagonals, that are actually in 45 degrees in the image, they're suppressed as well. So it's actually very interesting behavior. Now, if we go to the outside rim of this image, we see that most of the frequencies are passing. So that's fine. That's because I think the high frequency, they're not very high frequency changes, they're low frequency changes, and the sinc function passes them. Now, this covers the low pass filtering aspect of it and the fact that some frequencies are passed and the others not. But there's also something more interesting, which is the phase reversal. So in certain areas, in certain frequencies, if I look back at this function, I notice that certain frequencies, this function actually can take negative values, meaning that the intensity of the image can be reversed. And this is exactly what we see here as well. Look at this. Now, in this area, I see that this stripe is completely white in the original image. However, here, the stripe starts as white, but then it turns black. and then it turns white again, and then it gets suppressed completely. So you see that actually the phase reversal changes the content of the image. Now, this is quite interesting. So if I look at the summary of the step 1, when I acquire the image with the rectangular sensors, effectively I basically convolve the actual scene with a window function or rectangular box function. This first blurs the image, but more importantly, at the very high frequency areas, it may cause phase reversals in certain frequencies, really modifying the image content. So that's quite crucial to understand when we actually capture the image, digitize it, and use it for later on. This basically covers the effects of the first step. Now what we want to do is we look at the effects of the second step. So we said that the model for the sampling had 2 steps. One of them was integrating brightness over a cell window, and the other one was reading out values only at the pixel centers. So what does this mean? We will model this by simply saying that, so if I only look at certain points in the image, that must mean that actually I'm probing the function. And mathematically, probing a function can be modeled using a Dirac pulse. So a Dirac pulse is given by the definition here. So effectively, the function Dirac, delta Dirac, is actually 0 almost everywhere except at x0 in this argument. But there, it's not necessarily 1, but rather the integral of this function is 1. So in a sense, I can represent this function something like this. So basically, everywhere it's 0, and at x0, it takes the value of 1. But actually, again, doesn't take the value of 1, but its integral is 1. So it's slightly different notion. So why is this anything useful? Because this pulse can be used to probe functions, meaning that I can take a function f of x, I can multiply it with the delta Dirac, and simply take the integral. And the integral's value here will give me the value of f of 0. If I take a delta Dirac function, not centered at x equals to 0, but centered at x equals to x0, x sub 0, then the same integral will give me the value of the function f at x equals to 0. So Dirac pulse basically is used to probe functions locally. Discretization in the spatial domain, or basically just reading one value out of each pixel center, corresponds to multiplying an image with a Dirac train or a Dirac comb. Basically, a set of Dirac functions equally spaced apart at the centers of the pixels, okay, that actually multiplies the image. Fine. Now, this is quite interesting because I know that multiplying something in the image space corresponds to convolving something in the frequency domain. So what is the Fourier transform of the Dirac comb? Well, it is another Dirac comb, but now in the frequency domain. And so a convolution of the Dirac train means actually now I take the frequency information of the image and create periodic repetitions of it. So it's another duality of the discrete versus periodic case. More clearly, if we want to look at it in a schematic case, now assume that my function in the image space looks something like this. Now, if I multiply it with a Dirac comb, I will basically read off the values at the centers of the pixels. It will give me this function shown here. Its Fourier transform of the original image is given here. Now, if I convolve this guy with the corresponding Dirac comb, what I will get is this. I basically take the central area and repeat it multiple times. It actually looks very nice because, hey, there's no problem there. Because what I can do now is I can take this and simply cut this part out, use inverse Fourier transform to get my original signal. So actually, there's no problem in discretizing this guy and coming to here because I can simply retrieve it completely. But this is not always the case, because after you do the sampling, you lose some information. And in most cases, you may never get back the original signal. This really depends on the frequency domain representation of the original signal. If it is band limited, like the case shown here, then it's true that you can really retrieve it back. But then, to be able to do that, I really need to sample it at a certain rate. Specifically, if I look at the previous equations, the sampling of the Dirac comb in the image space were spaced apart by multiples of W and H. And that was really the size of the pixels that I use, or the size of the sensors. Its separation in the frequency domain is by 1 over W and 1 over H. So it's inverse. So that basically means the finer grid I use here, the smaller sensors I use here, this Dirac comb will be separated further apart, meaning that when I paste repetitions of the Fourier domain response of my image in different parts of the Fourier space, they will be further apart from each other. But if the sensors are close to each other, if W and H are actually large, if the sensors are large, that means that the Dirac comb separation, the Fourier transform domain, will be very small, meaning that I will basically have these and repeat them after another by basically pasting them very close to each other. In the end, there will be overlaps. Actually, this will lead to something very fundamental in signal processing, the sampling theorem. So if the Fourier transform of a function is 0 for all frequencies beyond some point, so U sub b and V sub b, basically meaning that if the Fourier transform is band limited, then the continuous periodic function can be completely reconstructed from its samples as long as the sampling distance, W and H, along x and y directions are such that they hold that W should be smaller than 1 over 2 U sub b and H should be smaller than 2 V sub b. If I don't do this, then I will basically introduce artifacts in the image the moment I sample it. So when we read of one value per pixel area, we're actually losing information in the image indefinitely. If the image is not band limited, which is almost always the case, whenever you have strong edges, meaning that you have very high frequency components, so the image will not be band limited, meaning that you will have response in your Fourier transform of the image at very high frequencies. More important, the information we lose is on the higher frequencies, meaning that whenever we actually do sampling of the image at certain intervals, we basically lose information about very fine details on edges, corners, and texture patterns. Now, that actually covers the first part in the digitization model, the sampling. The second part is the quantization. So we want to look at the intensity values that are normally, in the real line, and we want to use finite levels of gray levels to represent them. Effectively, what we want to do is we want to create k intervals in the range of all possible intensities and represent each interval with only one value. In terms of bits, I will use log 2k, log base 2, k number of bits to represent k levels. So there are certain design choices in this case. The first is the decision levels, or the boundaries of the intervals, and the second is the representative values for each interval. So if an intensity value in a pixel is between Zi and Zi plus 1, I will represent it with Qi. Okay. Now the simplest selection that's used very often is the uniform quantizer. So equal intervals between minimum and maximum values, intensity values that I expect. And to represent the interval, I simply use the mean in the interval. So Zi to Zi plus 1 will be represented by the average of these values. And very often, for the value k, I use 256. So I use 1 byte to represent each pixel. Pictorially, it has a very simple interpretation. Let's assume that in the x-axis, I have my actual intensity values that are in real line. And on the y-axis, I have the resulting quantized values. So I see that for certain intervals, I will use only one value. Then for another interval, I will use another value, and so on. And I will always use the average values of those intervals. Usually, to get a good picture using the uniform quantizer, you need large number of bits. So usually 7 or 8 bits per pixels are used. And if you have some idea about the probability distribution of the intensities you're expecting, P of z, you can actually design a much better quantizer. Effectively, you can minimize the expected loss of the quantization effect. So here my representative value, I simply compute the average error it makes, average square error it makes in a certain interval based on the probability distribution of seeing something there. So what does that mean? It means that assume that there are certain ranges of intensities that I never expect to see anything, then I'm actually okay to use very large intervals in those areas. If I now have other intensity areas where I expect to see a lot of intensity, a lot of pixels in those intensity ranges, then it's better to use smaller intervals to represent those values so that I basically have a much better reconstruction error or quantization error. Now the P of z, again, as I said, is a probability density function of intensities. And when we talk about the uniform quantizer, we assume that this is constant. So we expect intensity values at any range equally likely. So what are, again, repeating or basically recalling the effects of the quantization or under quantization in this case is normally we represent an image usually with 8 bits, so 256 gray levels. If we represent the same image with only 11 gray levels, what happens is we basically retain information in the high frequency areas, so retain information in the edges, but the smooth intensity transitions are disrupted. Instead of having the smooth transition in these areas, I see that actually there's there's discrete changes that are quite unpleasant. So small remarks on quantization. First, as I said, 8 bits are often used in monochrome images. If I talk about RGB images, color images, then I will use 8 bits per channel, so 24 bits in total. For special applications like medical imaging and satellite imaging, you would actually not use 8 bits because it doesn't really provide enough quantization levels to capture details, but instead you would use a finer quantization, either 12 bits or 16 bits, and these are actually used regularly.